So here's some more examples that go along with power. Just a couple more things to look at. Similar problems with a little bit of a twist. Here we got first, and this will be similar to the lab that we're going to do, is we got a jogger that's 60 kilograms running up a long flight of stairs in 4 seconds. Now, the vertical height of the stairs is 4.5 meters. We want to find power output in watts and horsepower, and then how much energy did this require. So work, as we said, or power, sorry, we'll get to work. Power is work divided by time. Now, work is energy. And the energy that's going along here is purely potential, right? We're starting at a point 0, and we're going to a height of 4.5 meters. And so since we're going up to that height, we're talking about a vertical distance. This vertical distance then can be with potential energy. So if I want to find work, I can find potential energy. Mass of 60 times g 9.8 times our height of 4.5 meters gives us a potential energy, in this case, of approximately 2,600 joules. There's some change there, but I'm going to round. Now, this 2,600 joules, that's our answer to B. How much energy did this require? 2,600 joules. We know the energy. So now, let's go to the work, or the power, which would be our energy of 2,600 joules, divided by our time of 4 seconds. A joule per second is a watt, so when we punch these numbers into the calculator, we get 650 watts. So that's our power. So now we got the answer to A, at least in watts. Remember, to go from watts to horsepower, right? We take our 650 watts and we divide it by 746 watts and 1 horsepower. And 650 divided by 746, 0.871 horsepower. So not even a horse worth of power there. Okay. Potential energy, if you can find it, is work, right? Because that's the work you're going to do to go from 0 to 2,600 joules. And then we can find how much the time it takes to get there. Obviously, it'll increase. Now, if I want to increase my power output, I just lower my time. If I can get up there faster, I'll be more powerful. All right? So walking upstairs requires less power than running upstairs. And we can feel that in our legs for sure. All right, power needs of a car. So there's 2 situations here. This first situation, we have a 10-degree steep hill. And we're moving at a steady rate of 80 kilometers per hour. The car has a mass of 1,400 kilograms. And we want to know the power required. All right? Now, there is a retarding force, okay, friction, of 700 newtons. We also have to consider gravity, right? Now, normally gravity goes straight down, but remember, on a slope, part of that gravity is going to try to pull us down this slope. Excuse me. So not only do we have friction at 700 newtons, but we also have the x component of our gravity that's pulling us down. And we talked about inclined planes. This came up. So our forces pulling us down are 2, okay? And we'll show you the math of how that works. Now, obviously, when we're talking about forces, it's Newton's second law. Net force is equal to ma. Okay? Now, our net forces. What forces are acting? Well, we have an applied force going up the hill. That's going in the positive. But we're going to subtract from that the retarding force, the friction, and the x component of our gravity. Okay? So we got gravity, force of gravity in the x. And that's going to equal mass times acceleration. We're solving for this applied force, okay? Why are we solving for this applied force? Because we want to find power, and we're going to use power is equal to force times velocity, because we have a velocity. We find force, we can find power. Okay, so here we are. So retarding force, so Fa minus 700 minus, and that's going to be mg sine of 10 from when we did inclined planes. The mass 1,400, g 9.8, sine of 10. Now ma, since we're moving at a steady speed, our acceleration is 0. So that's going to be equal to 0. Makes our math a heck of a lot easier. Now we just solve for the force applied. And again, I'm going to assume that you can do this. 3,100 newtons. And then I just take this and substitute it into here. I take this velocity and put it into here. Now, what I have to be aware of is that my velocity has to be in meters per second. So I got 3,100 newtons for my force. I got to convert my 80 kilometers per hour to meters per second. Again, that's something you should be able to do, so I'm just going to do it for you here, 22 meters per second. 3,100 times 22 gives me 68,000 watts of power. So the car needs 68,000 watts of power to do this. That's a lot of power. Now, what is this in horsepower? Well, I just divide this by 746 to get this in horsepower, and I need 91 horsepower. So if your engine is a 91 horsepower engine, you cannot, if your car is 1,400 kilograms, cannot make it up this hill, which you might find a different route, right? So now let's look at the next slide for part B. All right, part B talks about accelerating along a level road, okay? There's our initial and final velocities, and there's the time needed to pass another car. Again, same problems that we do have friction acting on us, okay? So now we're on a straightaway. Now, the difference in the straightaway, okay, and I'm going to draw you a quick free body diagram, is that gravity and normal force, remember, will counteract each other. So we have an applied force, and we have our retarding force, which we'll call friction. So normal force, and unlike on the slope here, right, we don't have to worry about gravity pulling us down a hill or anything like that. Those two are counteracted because of being on a level surface. So net force equals ma, force applied minus the retarding force, or the force of friction, is equal to ma. All right. So we know the retarding force. We're trying to find this force, so we can go and use this equation because we know the velocity. But now we have to find our acceleration. Acceleration is change in velocity over change in time. We know that, right? The key is you got to take your kilometers per hour and convert it to meters per second. So it's going to be 30.6 meters per second, right? Minus, and then the 90 is 25 meters per second. I want to subtract those two and divide by my change in time, which is 6 seconds. My acceleration then turns out to be 0.93 meters per second squared. Okay, so now I have an acceleration that I can substitute into here. The mass of the car hasn't changed. So here's what we got. FA minus retarding force of 700 equals 1,400 multiplied by 0.93, and I can solve for my FA. All right, my FA is 2,000 newtons. There's a little bit of change there, but again, I'm going to keep it rounded. So I have 2,000 newtons. I take my 2,000 newtons and put it in for force, so power is going to be 2,000. Now, which velocity do you use? The final or initial? Well, the key is that we want to pass this car, so we want to make sure that the car, right, can go at its top speed. So I'm going to use the bigger number, the 30.6, and I get my power in watts to be 61,200 watts. Divide that by 746, and I get my horsepower to be 82 horsepower. So on the level surface, if I get 82 horsepower, I'm golden. Again, Newton's second law, finding forces can apply to power. Force times velocity equals power. Just another use of this problem.